Welcome back to my YouTube channel, guys. Brown Guy Does Math. Yes, I'm brown, and I'm gonna do some math. Alright, we're back to our Calc 2 homework. Alright, I ended off at question 10 last time, and after watching the video and editing it for mad long, I realized I should probably do the questions first and then just go over them. That way I can save a lot of time. Hi, Rosa.
Where's Sophia?
Sylvia's in the other room.
Where's the room?
The other room. Go.
Am I
or
Nano's?
Nano's room, go. Okay, number 11.
I don't see a Nano.
Arctan of 1 over x, and it's not a indefinite integral. So I want to from 1 to 3. I'll do the tail. 1 to square root of 3. So first, I just rewrote it as 10 of negative 1, 10 to the negative 1 over x, and I used the thing method, I forgot what it's called, honestly. Integration by parts, which is uv minus integral v du, right? So I made u arctan of 1 over x, and the derivative of that would be, well, the derivative of arctan is 1 over 1 plus, since our x value here, right, is 1 over x, same applies here. It should be x squared, but since our x value here overall is 1 over x, we just carry that on. And then multiply that by the derivative of 1 over x, right? It's just right here. That is just negative 1 over x squared. And then dv is just dx, right? Right here. And the integration of that, which is just v, this is a v by the way, is x, yeah. And you use this rule, you should get x times arctan, right? U times v, arctan of 1 over x times x, right here. And well, this is gonna be integrated because that's just part of it, and then should be plus because of the negative that's carried on here, right? I just didn't write the negative here, I just put it over here. I made it a plus. Yeah, and the integration of 1 over integration of v du, which is here, v du. This cancels out, right? Wait, my bad. I just multiplied this by x squared at x squared. It doesn't change the value because it's, x squared divided by x squared is 1. And that helped me get rid of this, the x squared from the denominator. And I'm left with, if I distribute this here and here, I'm left with x squared plus 1, right? And on top is x squared. Okay, here. And here, what is it? It was v times du. Our du is this whole thing, and our v was x. That's why I was able to cross out the x squared, and I was just left with 1 over x here. And then I'm able to cross out this x and this x squared, and I'm left with x over x squared plus 1. And I gotta use after that, what did I do after that? Oh yeah, this is just a simple substitution over here, right? You can make this the u value, right? X squared plus 1, and then if you do that, you're left with du over 2x is equal to dx. You can substitute that for dx over here, right? dx substituted, and then that crosses out the x. You're left with 1/2 over here, right? You can bring that outside the integration, and just integrate 1, and you're left with 1 over u, right? And that's just ln of just ln of u. And our u value, when we substitute it back in, is x squared plus 1. And then, yeah, Now it's just a matter of plugging in the values, right? First is square root of 3 times arctan of 1/3. Well, if you see here, where is it go? Well, this is our professor taught us. Just a quick little thing. Is 1/10 of thing is 1/3. Yeah. So tan of tangent of pi over 6 is 1/3. So the inverse of tan of 1 over, wait 1 second, 1 over square root of 3 would give us pi over 6, right? And same thing with this, right? What's tangent of what? Tangent of what gives us 1? Tangent of pi over 4 gives us 1. Okay? And here should be my plus, right? Plus 1/2 of this. You just, oh yeah,
Bluetooth.
Rosa, what are you doing here? Hmm? Go. Yeah, she's far. Go. Um. Same thing applies here. You're left with 1/2 of ln plus square root of 3 squared, which is just ln of 1 plus 3, which is ln of 4. And over here, ln of 1 plus 1, which is just 2. And then this should be your answer. Oh. Yeah, I think if you simplify this even further, you should get this same answer over here. But yeah, that's what I got. I'm not trying to do all that work. It's crazy. But that's just the main gist of that question. Alright, number 12. Theta cubed times cosine theta squared of d theta, right? So you can split this theta cubed into theta squared and theta, right? Then you can go into then you can just a simple u substitution, right? Over here you make u of theta squared, and then you're left with du is 2 theta d theta, and then you're left and you get d theta is equal to du over 2 theta. You can substitute that in for d theta, right? It's going to be du over 2 theta. Then you're left, and you can cross out these thetas, right? And now you're going to be left with u, right? Our u value is theta squared. So these are theta squares right here. U times cosine u over 2. We can take out the 1/2, over 2, which is right here, outside. And then after that is just, you can use the shortcut way that our professor taught us, our Shofiko Sasa, W guy. Since cosine, we know that is a repeated function, right? It alternates between sine and cosine. We know we're gonna integrate that, and our just what do you call this function? Just regular expression, derivative, polynomial, right? A function is just u. So plus u multiplied by the integration of cosine u, and that's just sine u, right? So, and then now you do integrate the u, which is, and then you put the negative here. U integration of u is 1, and you take the integral of this, and you're left with cosine, negative cosine u, and you just multiply this with this, and the negative 1 with the negative cosine thing, and should be left with 1/2 of u's u sine u plus cosine u, and then obviously you just plug it in after that. Yeah. If you want the theta, you can change these values by substituting in for the theta, right? So you can do like, oh, pi squared, whatever, and then, but that's too much work. I don't have time for that. You can just substitute it back in for theta. Oh wait, no, that is what I did. My apologies. Yeah, that's what I was doing. Okay, because yeah, I was like, why would it be pi squared? Yeah, so our original integration was telling us to find from square root of pi over 2 to square root of pi, right? So when we substitute in for u, right, it's theta squared, right? So if we do that, if we plug in our x values into theta for u, we get that theta squared, which is pi over square root of pi over, no, square root of pi squared is just pi, and square root of pi over 2 squared is just square root of pi over 2, right? And then we carry this value on forward and just keep our u value, and then you just simple plug in after that. Pi times cosine of pi, well, that just crosses out because sine of pi is just 0, and cosine pi is -1, right? So -1 times 1/2 is -1/2, and then -1/2 times pi over 2 times pi over 2, sine of pi over 2, and that is 1, right? So that's gonna be 1 times, oh, plus, yeah, cosine of pi over 2 is 0, so that crosses out, and you're left with -1/2 times pi over 2 multiplied by 1. That's just 1. So you're technically just left with, yeah, -1/2 times pi over 2, and multiply these together, you're left with negative pi over 4. And that should be your answer. Yep, that's the answer. Alright, number 13. Okay, this was crazy, man. Cosine to the 7th power x times sine to the 5th power x, right? Okay, what did I do here? I split up the sine to the 5th into sine to the 4th and sine x, right? That way I can use our trig substitution, our trig identities, because we know that sine squared x is 1 minus cosine squared x, right? That's just like, Pythagorean theorem identities, stuff like that, or I forgot where the origin came from, but so you can rewrite this as sine x, you can rewrite as sine squared x to the squared, and that's what I did over here, right? I just substituted in for sine squared x, which is right here. Just skip that step. And, so now you can make, so since we have cosine here, we know the derivative of cosine is going to be sine. It doesn't matter the negative or positive. We can make that our u value since we're trying to get rid of this one sine here, right? So that's what I did. That's exactly what I did here. U is cosine x. Du is going to be negative sine x. And that's exactly what I did here. This I substituted in for dx. Our dx is du over negative sine over x. These sine x crosses out. The negative I carried over here. I just bring it outside the integration, and I just change the cosines to u's, so it's easier to deal with. Distribute, do the square. 1 minus u squared, the whole thing squared, is going to be 1 minus 2u squared plus u to the 4. You distribute the u to the 7, you're left with u7 minus 2u to the 9 plus u to the 11 du. Okay. Oh yeah, just one quick note. I think it's mainly a note for myself as well. The reason we kept pi over 2 and 0, like, you know, it's the same value as this, right? The reason this was different here was because we substituted in for u, right? And that's how we were able to get rid of this square root, because of the square over here, right? And that's why we were able to substitute in for u. We were able to keep this u, right? This u, right? We didn't plug in, you know, theta squared back over here. We didn't write theta squared here or theta squared here. And we were just able to use these two values because we changed these values. But over here, since we kept these values, you know, it tells us that we need to plug in, substitute back in for u. Okay, if we don't do that, then we have to plug in these values for u, you know, cosine of pi over 2, and then cosine of 0, and then it could be like, you know, 1 to 0, because cosine of pi over 2 is 0, and cosine of 0 is going to be 1, so it's going to be 1 to 0. And then we could just keep our u values. I mean, it'll give us the same answer. But I don't know why I didn't do that. I just plugged it back in for u, and our u value is cosine, so cosine to the 8, cosine to the 8, yeah. Oh yeah, you integrate this first, obviously, and then you, yeah, I just kept the -1 outside because it's too much distribution. It's gonna confuse me. Yeah, do the word, you know, plug these in, and then subtract it by plugging this in. A lot of work. I go front. The highest common, yeah, the greatest common GFC of this is 120. So yeah, that's that. It's just 1 over 20. Yep, that's 1 over 20. Okay, number 14. Sine squared, 3 sine squared t of cosine t, cosine to the 4t. Excuse me. You know. Yeah, so you can bring out the 3 from here inside, outside. It just doesn't really matter, constant. I split up the cosine to the 4. I mean cosine squared, cosine into cosine squared, cosine squared. And then now we know that, yeah, I can take out the square from here, but since both of them are being squared and then being multiplied. And one of our other trig identities, right? Wait, why isn't it going down? Is sine x times cosine x is 1/2 of sine 2x, right? And that's exactly what we did here. We took out the square, right? So we're left with I'm sorry, I need to go back and look at this one more time. Yeah, 1/2 of I mean, this is just 1/2 times 2, which is just 1. It doesn't really matter. I don't know why I did that. It's not really necessary. But yeah, sine t, cosine t is the same as 1/2 of sine 2t. And then we can also do the same, I believe, for our cosine identity, right? Yeah, because cosine squared x is the same as, here, 1 plus cosine 2t over t. That's also another trig identity that our professor showed us here. Cosine squared is 1 plus cosine 2x over 2. Okay, I mean, after that it's pretty self-explanatory. You just There's a lot of trig substitution. So square root that, square root that. Square root of, no, not square root. Square this, and then square that, right? You're left with 1 over 4. Bring out the 4 here, and then you're left with sine squared 2t of cosine squared t dt. And I want to change it. The reason maybe we had to change it was because of this 2t, right? This 2t, we're able to distribute this sine squared 2t into this, right? I just brought this, since this whole thing is being multiplied, I brought this 2 outside, and that made it 3 over 8. You should get sine squared 2t. Yeah, integration of that, and the integration of sine squared of 2t times cosine 2t. Since we're just trying to get rid of this cosine, we make our u value our sine 2t. So our dt is du over cosine 2t, right? And we're able to get rid of that. We just substitute for u squared, right? U squared. And this cosine 2t crosses out, and you're left with this 2 over here. Excuse me. So this becomes a 16, and I'm pretty sure this becomes a 16 as well. Okay. Yep, I bring it down here. Trying to figure out what I'm doing. Yeah, just integration of 1. Yeah, how did it become a 1? Oh yeah, my apologies. This, I gotta be more organized. Let me go step by step. So this sine squared 2t becomes a 1 minus cosine 2t, right? 2 times 2t. Because that's just another trig identity. We learned sine squared of x is 1 minus cosine 2x over 2. And our x value here is 2t. So we substitute for x, which is 2t. And you're left with that. And I just pretty much broke up this whole integration again. So 1 minus cosine this, yeah. So integration of 1 dt and integration of cosine 4t. The reason is 4t again was because we substituted 2t for x, and 2 times 2t is 4t, which is right here. So that, yeah, the integration of 1 is just x, and the integration of cosine 4t is gonna be sine 4t over 4. Well, and okay, the reason I crossed this out here was because the integration, if you plug in the values, sine of 4 pi, which is just, the same thing as 0, or 2 pi, is going to be 0. So this whole thing is 0, right? Because 0 times 0 over 4 times whatever it is just 0. And same thing here. Pi, and then, you plug in 0. Pi and 0, they're pretty much the same for sine. They both equate to 0. So these crosses out, and you just plug in sorry, my eyes. You plug in pi for x, which is, and then multiply by 3 over 16. Pi over 16. So you're left with 3 pi over 16. That's your final answer, which is right here. Oh my god, my eyes going crazy. Okay. Now we're on number 15. sine squared times cosine squared. Again, we're gonna have to do a lot of trig substitution. Just same thing we did last time. Just bring out the squared outside because they're both being squared. And we know that sine x times cosine x is cosine, 1/2 times sine 2x, right? That's what we did here, right? Yeah, 1/2 times sine 2t, or here. 1/2 is here. And then after that, you can bring out the 2, becomes a 4 because of the square. Just distribute the square. This becomes sine squared 2x, and then bring out the 1/4. And then you can substitute in another trig identity for sine squared 2x, right? So, well, if you get sine squared x, it should the trig identity for that would be 1 minus cosine 2x over 2, and in our case our x value is 2x, so 2x, right? And our x value is x. We plug this in over here, and then you should get 2 times 2x. So you're left with cosine of 4x over here. That's how this 4x came about. You can bring out the 2 again because the whole thing is being divided by 2, and just bring it over here. 1/2 times 1/4 is 1/8, and you can just split up the integration. The integration of 1 is just x, right? So you get x over 8 over here, and then integrate, plug in the values over 2, find the area under the curve for these values, and this is simple integration. Integral of cosine is just sine 4x over 4, and 4 times 8 is 32. That's how I got this 32 over here. Now you just plug in. Well, 0 over 8 is just 0. That's why I didn't even bother writing anything else. And then pi over 2 over 8 is just pi over 16. So I could have written pi over 16 over here for this, but oh yeah, I did write that. I explained how I got that over there. And then sine of pi over 2 is just 1. Oh right, but it's 4, so it's 4x, right? So 4 times pi over 2, that's the same thing as 4 pi over 2, which is just the same thing as 2 pi. And the sine of 2 pi is just 0. That's why I crossed this out. Minus, sine of 0 is just 0 again. So your final answer is just this, and that just simplifies to pi over 16. Yep, pi over 16. It shouldn't be too challenging. Alright, yeah, I was a bit freaked out on this one too. But a general rule that I picked up from a video I watched. Where's that rule? Where's that thing? Oh, here it is. If you have secant and tangent in a tan and secant in an equation like the one we have right now, or even in this one, right? If you have even power of secant, save a secant squared. Well, you might not be always able to do that because, if it's just secant by itself, but that's just the general rule. And if it's odd amount of tan, then save as secant and tan x. Here is a good rule to remember. So we had odd amount of secant x, which was secant to the 6th, right? So I saved a secant squared. I can write the trig identity. You can rewrite this secant to the 4x to a secant squared x to the 2nd power, and secant squared x, its trig identity is 1 plus tan squared x. to the second power because of this. Now you can make your u value tangent because we know the derivative of tangent is secant squared, right? So our u values are our tangent becomes u, right? And our derivative of u is secant squared here. And we substitute in for dx. Substitute for dx is going to be du over secant squared. This secant squared crosses out, cancels out, just becomes 1. And you can just integrate after that. And integration of, oh yeah, my apologies. Just obviously fold this. After you fold it, you should get 1 plus 2u squared plus u to the 4, and then distribute this thing. And you should get u to the 4 plus 2u6, u8, and simple integration after that. And then you can plug back in the u values. The u, which is 10x. And this should be your final answer. Yep. Alright, number 17. Oh, it's another 10 secant ones. This time, still the same. We can literally do the same thing again. Secant to the 6 is an odd number, right? So we want to save a secant squared because we know the derivative of tangent is secant squared, right? So I break up the secant 6 into secant 4 secant squared, right? Do the same thing again. This becomes 1 plus 10, this whole thing, 1 plus 10 squared x to the second power because of the 4. Again, make the u 10x, cancels out these, these secant squared. Secant squares, oh, my apologies, there should be a 2 here. And then foil this. You're left with 1 plus 2u squared plus whatever the shenanigan. Distribute, blah, 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 blah. Integrate, and you're left with that. Boom. You can pause to look at it. Yeah, I tried to color code most of these, and then I just got lazy. Okay. The next question, 18. Evaluate the integral of sine squared 3t over t squared. Okay. This was kind of freaky. But if you just follow through with it, it's not too hard. I think if you just start doing something, you'll figure out a pattern. Okay, so what I did was, it turned out to be just simple u substitution. So I made the u value 3 over t, and you can rewrite that as 3t to the negative 1 power, and the derivative of that is negative 3t times negative 3t times t to the negative 2 power dt, and isolate dt, so we can substitute it for dt over here. You substitute for dt, you get du over 3t to the negative 2 power, right? And this negative 2 crosses out. T to the 2, t to the negative 2. If you add them up, becomes t to the 0, t to the 0 just 1, and you're left with just negative 1/3, right? Negative 1/3, because 1/3, negative 3 is on the bottom, of just sine squared of u. After that is just basics again. We go back to our trig substitutions. Sine squared u, or x, whatever it is, it becomes 1 minus cosine of 2u, right? Bring out the 2 on the outside, and that becomes negative 1 1/6, 1 negative 6, and you can just, since they're subtraction in the middle, just break it up. It helps me. but you don't have to do all this stuff. Like, I just read it out because I'm still, like, new to integration. But yeah, the integration of 1 du is just u, and then multiplied by negative 1/6 is negative u over 6. Hold this whole thing right here. And the integration of negative cosine u is just negative, no, it's negative cosine u, right? It's gonna be, hold on, sine, integration of that is just cosine. Yeah, just positive. Yeah, just positive. It'd be negative sine because this negative carries on. Negative sine x, yes. So negative sine 2u over 2 divided by 2, and then multiplied by negative 1/6. So it'd be negative 1/6 multiplied by negative sine over 2u over 2. This 6 times 2 becomes 12, and yeah, and the negative times negative, negative 1/6 negative sine becomes positive over here. And then we plug back our u value, which was 3 times t to the negative 1 power, and yeah, that's what you get. Your answer. Now it's just a matter of simplifying. You can do that. Yeah, negative 3 over 6. It's just 1/2. T to the negative 1. You can bring that down, get rid of this negative, and you're left with negative 1 over 2t. Same thing here. You should be left with 6 over t, because t is the same thing as, yeah, sine of, yeah, that's it. And then don't forget the plus c. Now we're on number 19. ln of square root of x. This was kind of weird. Like, I was freaking out at the first, because I'm like, oh, square root of ln of square root of x. I never heard that before. But we can use our ln properties to help us here. Rewrite this as ln of x to the 1/2. Obviously, the property allows us to multiply ln by if the inside value is brought to a power, right? So if it is brought to a power of 1/2, we can bring the outside and just multiply with ln. So now you're left with ln x times 1/2. 1/2 times square integration of ln x dx. Now you can use your integration by parts. Make u our ln, and du becomes 1 over x dx, and our dv is just 1 dx, just this part. Well, I just wrote 1 to help for visualization. And you multiply that, x times u times v, which is ln x times x times ln x, minus integration of du v, right? V du. Our thing value is just x times 1 over x dx. These x cancels out, and you're just left with the integral of 1. The integral of 1 is just x. And you distribute the 1/2, and you should be left with x ln x over 2 minus x, this thing. If you do the integral of this, just x times 1/2, which is x over 2, plus c. And that should be your answer. That's weird. Oh, I think this is the same thing, right? Because you can do it's the same thing. It's the ln property. we can do this times ln of x. You can bring in this on the inside. This would be x times ln of x 1/2, and same thing, and that's just x times ln square root of x. Yeah, nothing to worry. That's the same thing. You can write this, or you can simplify it to get this answer. I won't even call that simplifying. That's just complicating, honestly. Oh, right. Number 20. This one. Ooh. It would have taken a very long time if you were just to use this whole integration by parts. Hi, Rosa. You need something, Rosa?
Yeah.
What do you need?
Trig ball. I want ball.
Okay.
I want this.
Yeah, so luckily in this case we got a polynomial, right? Or Rosa, you can add box here. Go to the other room. You can take it to the other room. Go. This we can integrate to 0, right? And multiplied by a repeating function, e to the z. Rosa, go to the other room. Give me. Don't open it over here. Go to the other room. I'm doing something, Rosa. Yes, Tanmai Bhai will help you. Go.
No.
Yes, he will.
No, I will open and put it.
Okay, you can do it by yourself. Okay, I'm sorry. Go ahead. So you just differentiate the polynomial, right? Until you get to 0, and you don't do that. Yes, I will open the door for you. Go, here you go. It's over there. My apologies. Alright. So you keep on differentiating this, but make sure you alternate between positive and negative, positive and negative, positive and negative, and so on, until you reach 0, which is we did over here, and you don't need to do the 0 one. And you just keep on integrating the repeating function, right? In this case, we got really lucky. It's just e to the z. Sometimes it could be like e to the 3z, and you'd have to like divide it by 3 again, and then divide that by, and then carry the 3z divided by 3 again, and so on and so on and so on. But here, just e to the z, and integration of e to the z is just e to the z. Same thing as ex, whatever you're used to. And at the end, after that, you multiply this by the value of the whatever you get for after integrating the repeating function, and bring this over here, integrate it again, you get that, and multiply this derivative by the integral of that, integral of this, right? It's just like this. Yes, this repeat. It's just this function repeated, or this pattern repeated. Multiply, bring down, multiply, this, and then bring down here, multiply this with this, and this is exactly what you should get. Positive z cubed times e to the z minus negative 15z squared times e to the z, and then plus 30z times e to the z minus 30 e to the z plus c at the end, because this is indefinite. Yeah, that's the answer over here as well. Oh, that's cool. Whoa. My bad. Alright. 21. 4 times sine squared times cosine squared. Okay, yeah. This one again is a lot of trig substitution and stuff. You can obviously bring out the constant over here, right? Bring out the 4. And separate the cosine cubed, because we are most like, because we want to keep our sine value in this case, right? Because again, cosine and sine, they're like repeating functions, so we can use that to get rid of this. So we want to turn this into a sine, right? All of them are sine. So what do we know about the trig identities? Cosine squared x, right, can be written as 1 minus sine squared x. Again, Pythagorean theorem identity or something like that. And then you can distribute. I mean, you don't even have to distribute here. It's just a lot of work. You can save yourself by just making u or sine x here, right? That's exactly what I did here, right? So once you make your the sine x your u value, right? You can do the derivative of sine, and you should get du as cosine x dx. And once you isolate dx, you get du over cosine x, and you can substitute that for here, right? And then you're able to cross out the cosine x here, and then you should be left with your u values. Substitute in the sine x's for u. Now you can distribute the u squared here. It saves you a lot of time instead of like distributing this and then like making the u's and stuff. It's a lot of work. After that, simple integration of u squared is just u to the 3 over 3, and then this one is u to the 5th over 5, and then obviously distribute the 4. So 4 times this, 4 times that, and then plus the c. Very good. Yeah, this one was crazy. Integration process was easy, but then this whole substitution thing got me annoyed. Okay, so you have sine to the 5th x dx. You can break that up again, right? So now remember, it's always just, if you're just having these by itself, or even if it's cosine, 5th x, right? You want to save one on the outside, because we know that sine and cosine, right? They're like alternate, they just alternate between each other, and they're repeated functions. And when we like differentiate or integrate, what did I undo? Go back. So that's exactly why I saved the sine x over here, and then I put sine to the 4x. Here we can bring that. We can break it apart, right? Sine squared x to the second power, and then bring in our trig identity. Sine x squared is the same as 1 minus cosine x squared, right? And I'll make our u value u value cosine this time, because again, as we know, derivative of cosine is negative sine x, right? And that's how we'll be able to get rid of this sine x over here. And that's exactly what we did here. Substitute cosine for u, and then substitute dx for du, right? Our dx becomes du over negative sine x here, you see, once you isolate dx. And you're able to cross out this sine x, but you're left with a negative. So bring that out on the outside. And then you should be left with 1 minus u squared to the second power. Foil that easily, becomes very easy. 1 minus 2u squared plus 4u. This is just this foiled up, or foiled down, whatever we're going to call it. And then, yeah, just distribute the negative if you want, because these are just easy numbers to work with. And then the 1 becomes just a u, and the integration of 2u squared is 2u 3 to the 3 over 3, same with this. And then the annoying part is the substitution. So we know that it's cosine of 0 is always gonna have a value, which is 1, right? So whatever this is gonna, honestly, yeah, I should have changed these values. These would have been a lot easier to work with. because this would have become 1, and this would have become square root of 2 over 2. Could have saved a lot of time, so you should probably do that. Dang, there's so much time on this. But yeah, substitute this, substitute that. You could save yourself if you change these values. You can probably save yourself potential errors you can make, and that's always good. Yeah, and you should be left with this. Yeah, I didn't even bother. I didn't even bother. I can't even speak. I'm so frustrated. Things took so long. I didn't even bother simplify. This is the answer. I just put this. I'm pretty sure I should simplify to this because I got the 815 right over here. Alright, next one. Number 23. 3 cosine squared theta d theta. Okay, that shouldn't be too hard. Right? Bring out the 3. Substitute in cosine squared theta for... Oh, okay, that's what I did, yeah. Well, since it's squared, right, we're trying to get rid of this. So substituting in cosine squared theta for 1 minus sine squared theta is really not helping us at all, right? Because because of the sine square, still got that squared theta, this square. We're trying to get rid of that. So we use the trig identity just for cosine squared theta, which is 1 minus cosine 2x over 2. Bring out the 1/2, 3 over, this becomes a 3, the 3 becomes 3 over 2, and then it's just simple integration after that. Right? Integral of 1 is just x, and then integral of cosine 2x is sine 2x over 2. And then you can distribute, well, I already set these two apart, so you can bring them back together if you want. That sine of 0, it's just plugging in. You know what to do after that. Plug in your top value, and then plug in your lower boundary. This thing just crosses out because 0 times x is 0, and sine of 0 is just 0. And then same with over here, 2 pi over 2. Since it's 2x, 2 pi over 2 is just pi, and sine of pi is also 0, right? And you're just left with 3 times pi over 2, which becomes 3 pi over 4. And that's your final answer. Alright, number 24. Integration of sine squared of 2 theta. Again, we're going to get rid of this 2, right? We're going to get rid of the square. So we plug in the trig identity for sine squared, which is 1 minus cosine 2x. And our x value here, right, is 2 theta, right? So 2 times 2 theta, 2 times 2 theta becomes 4 theta, or cosine 4 theta. And then you can bring out the 1/2 because the whole thing is being multiplied by 1/2, right? And then the integration of 1 becomes theta because we're integrating in respect to theta, not x in this scenario. And minus the integration of cosine 4 theta is going to be here. Is going to be sine 4 theta over 4, because the derivative of sine is cosine, right? Over 4. You could have saved your... I don't even know why I did this. I think I was tweaking. yeah, just plug in the values for theta. 0, right? 0 is just 0. I don't even write that. And the upper boundary is 1/2 times 4 pi. I mean pi over 4. So that's just, you know, that's just pi over 8. Yeah. Oh, and apparently, oh yeah, that makes sense because it's 4 theta. 4 times pi over 4. These 4 cancels out, and you're left with sine of pi. And we know that sine of pi is 0, so this has become 0. It doesn't even matter what we're dividing by. And sine of 0, I mean, is just 0. So this whole thing crosses out, and you're just left with this thing, which is pi over 4 times 1/2, which is pi over 8. Yep, and that's your answer. Alright, 25. 25 is tan squared x times cosine cubed x. Okay. What did I do here? Oh, yeah, this is relatively easy. You can plug in, well, you know, we know tan is equal to sine over cosine, right? So since it's tan squared, we can substitute that in for sine squared x over cosine squared x. And then that, after doing that, we can see that, okay, since cosine, oh, sorry, there's cosine squared here and cosine cubed here, and that's the square should cancel out, and you should be left with just sine squared, right? Sine squared times cosine x. And then obviously take out, I mean, it could have been either or. No, it couldn't be either or. It has to be sine. Make your u value sine x, so our du becomes cosine x dx, and then you can substitute that for dx to get rid of the cosine, right? And then our u becomes u squared because the sine was being squared, and then it's just simple integration after that. It's just u squared du, which is u cubed over 3 plus c, and plug in for u. That's your answer. Is that the answer? Yes, it is. Okay. Yeah, I tried doing something here. I don't know. Failed. Oh yeah, we go back to that little tip from earlier. If this just secant and tan, if there's odd amount of tans, which you do have over here, just one, then save a secant and tan x. So that's exactly what we did here. We broke up the secant cubed into into secant times secant squared. So we saved this over here, right? And then after we do that, we were able to make our u value secant, because the reason we saved this tan times secant was because we know the the derivative of secant is what? Is tan times secant, or secant times tan, same thing, right? So that's how we're able to get rid of these tan times secant, because that's what we saved it to get rid of it through u substitution. So secant, our u is secant x, our du is secant times tan x dx, and we can substitute our dx for this, right? And then this cancels out our tan x secant x, and you're left with u squared du right here. And after that, simple integration again, plug in for u, integrate it, and then plug in, and yeah, that should be it. Okay, number 27. 2 times tan cubed x secant x dx. Yeah, so take out the 2. Again, odd amount of tan, right? So we want to save a tan x secant x. You can substitute this trig identity for tan squared x is secant squared x minus 1. We learned that from our notes, right here. And it's just the same thing, same process as 27 applies to 28. Oh, I'm sorry, 26 applies to 27, right? Write this out, secant times that. It's going to be secant squared x minus 1, make our u value secant, and then the du becomes tan x secant x dx. Plug in for dx, cancel out this tan x secant x, and you're just left with u squared minus 1, and the integration of that is just, oh, did I make a little mistake here? I think I did. Yeah, my apologies. I was supposed to distribute the 2 to both. There's supposed to be a 2 here. Well, let's write it out then. Okay. Yeah, and then plug in for u. You should be good. That's your final answer. 28 is tan to the 4th power t, and it's not indefinite. It's kind of annoying. But so what I did was I broke up 10 to the 4th into tan x squared, and again I used the trig identity for the tan x squared, and I got secant squared x minus 1. Distribute the tan x squared into that, and you should be getting tan x squared times secant squared x. I think was there? No. Yeah, our u value is tan because we know the derivative of tan is secant squared, right? So we can get rid of the secant squared here. So, well, there should be a dx here, my apologies. So that's why when we plug in for dx here, du over secant squared, this secant squared crosses out, and you're just left with tan u squared, which is tan, right? And this would be and the integration of u squared is just u cubed over 3. And then now what we're going to do here is just, what is this? Well, yeah, this is a simple integration, right? What's the integral of secant squared? It's just tan x, right? And what's the integral of 1? It's just x, since we're taking 2 with respect to x, dx, right? So, and then distribute the negative, right? Don't forget that. Yeah, distribute the negative, and this becomes a negative tan x, this becomes a positive, right? Positive x. And then after that is just substitution. So annoying. There's just a lot of substitution. I'm not really good with that, so I always write everything out to avoid making a mistake. Pi over 6, right? That's what it was. Yeah, pi over 6. Tan cubed of pi over 6 is 1 over square root of 3. That cubed is just 1 over 9. And you can see me break it down here. It's quite self-explanatory. You can pause the video and look at it. I think I made it pretty clear. Well, I would want you to know it goes from here to here. just know that tan of 0 is just 0. And this cancels out this part, the lower boundary. Okay, question number 29. This, I did it in class with the professor, and this is the answer he got. And that's the answer I got as well. But he said there was another way of doing it to get this exact answer. And I tried doing that over here. But I'm like, yep, screw it. Like, something wasn't mathing. But this is not too hard either. Again, it's just a matter of knowing, just finding, just knowing, you know, the derivative between, like, the things you're working with, right? If you got tan, we need to know that the derivative of tan is secant squared. So we can rewrite our, we can break this up into these two, right? Tan squared and tan cubed, and then and then substitute our tan squared for secant squared x minus 1. Obviously, distribute now, right? And then now you're left with tan cubed secant squared x. Make your u value the tan x, because we know the derivative of tan x is secant squared x. That's how you'll be able to get get rid of the secant squared, and you should be left with u cubed just for this side, right? And this side we're gonna do it later. We're gonna do with this side separately because it's tan cubed. Okay. What we did here was plug back in. It was pretty much the same, because split up this cubed, tan squared times tan x, and then secant squared minus 1, distribute again. You're left with tan x times secant squared x dx plus integration of x tan x dx. Well, make sure you distribute the negative. That's what I did here, since, you know, this, I distributed this right here and here. So this negative became a positive over here. Again, u is tan x, du is secant squared dx, gets rid of the squared secant x squared, and you're left with integration of u, which is negative integration of u, which is this. And we know that integration of tan x is ln of secant x plus c. And that's your final answer. Maybe you can rewrite this somehow to make it like that. Who knows? And the last one, finally. Sleepy. Is square root of 1 plus cosine of 2x. Right? This seems very awfully familiar, right? We know, remember our cosine identity? It was cosine squared x is equal to 1 plus cosine of 2x over 2. So all we're missing is this divided by 2 here, right? And that's exactly what we did. We just made up our own. You can multiply this by 2 over 2, right? Bring out the 2 here and keep the divided by 2 here. It's still the same. We haven't changed the value. We just made it where this becomes similar to our trig identity of cosine squared x, right? And that's how we're able to get this cosine squared x over here because of this, right? And okay, before we do that, I brought out the 2 over here, but the reason it's square root of 2 is because of this square root here. Yeah. So, and then the cosine squared, it cancels out with the 1/2, and you're just left with square root of 2, square root of 2 times the integral of 0 to pi over 4 of cosine x dx, and that's very simple. Come on. That's just sine x, right? The integral of cosine x is sine x, and plug in the lower boundary, upper boundary. Lower boundary of sine 0 is just 0, so this cancels out, and square root of 2 times pi sine of pi over 4. Sine of pi over 4 is square root of 2 over 2, and these square roots cancels out. You're left with 2 over 2 over here, and that's just 1. Yeah, that's the whole video, the whole 30 questions, and yeah, I hope that helped. Brown guy does math. I'll probably return when there's homework number 3. Okay, I love this. God dang it. Homework number 3. There you go. I'm going to upload this soon. Alright, take care. Bye-bye.